Hey everyone! So, if you've crushed single variable calculus, you're probably wondering, what's next? Well, get ready because we're about to jump into the next dimension. Today, we're taking everything you know about finding area and leveling it up to find volume with double integrals. Okay, let's take a quick trip down memory lane. You remember the definite integral, right? How we used it to find the exact area tucked away under a curve? That was a classic 2D problem with a 2D solution. And this is the whole game right here. It's the core idea. Just like a single integral gives us the area in a 2D plane, a double integral is our tool for finding the volume under a surface in 3D. See the notation? We literally just add a second integral sign. It's a super logical and powerful step into that third dimension. So here's our game plan for today. We're going to see how area connects to volume, get the official definition of a double integral, run through the key rules you need to know, work through a few examples so you can see it in action, and then wrap up by learning how to find the average value. All right, let's dive into our first section. We're going to build directly on that foundation you already have from single variable calculus. Let's think about this for a second. Calculus gave us this amazing tool to find the area under any kind of complex, squiggly curve. But what if we're dealing with a 3D surface, something like a rolling hill or a draped sheet? What tool do we pull out of our mathematical toolbox to calculate that volume? And that question leads us directly to the star of today's show, the tool that gets the job done. So here it is, the formal definition. A double integral gives us the signed volume. Now, don't let that word signs trip you up. It just means that if the surface dips below the xy plane, we count that volume as negative, exactly like how area below the x-axis was negative. And that little dA at the end, just think of it as one tiny, infinitesimal patch of area on the floor of our region. But let's be real. Let's cut through all the jargon at the end of the day. What is a double integral? It's how we find the volume under a surface. That's the main idea. If you remember one thing, remember that. Now, before we jump in and start calculating, we've got to know the rules of the road. So let's go over the essential toolkit for double integrals. And the great news is, these should look really familiar. They're basically the same rules you already know for single integrals. You can split up addition, you can pull constants out in front, and you can add up the volumes over different regions. We also get this handy new formula for the average value of a function, which we're definitely going to use in a bit. Okay, enough theory. Let's get our hands dirty and see how this all works in practice with a couple of examples. We're going to start with a nice, simple case. Let's find the volume under a perfectly flat surface, a plane at a constant height of 5, sitting over a simple rectangle on the floor. For this one, we don't even need calculus. It's just a box. The height is always 5. The area of the rectangular base is just 2 times 3, which is 6. So the volume is simply the base area times the height, which gives us a clean volume of 30. And this is the exact same answer a double integral would give us. It's a nice little sanity check that shows how these new ideas line up with basic geometry. Okay, but what happens when the surface isn't flat? For a curved surface, like z equals x squared plus y, we'll approximate the volume using a Riemann sum. The idea is to slice our base into 4 smaller squares, and then find the height at the exact middle of each square to create 4 little rectangular pillars. This table just breaks down the math for each of our 4 pillars. We find the midpoint coordinates for each little square, plug those x and y values into our function, and that gives us the height of each box. You can see those calculated heights over in the value column. So to get the total estimated volume, we just add up those 4 heights we calculated, which gets us to 9. Then we multiply that sum by the base area of each of our little squares, which in this case is just 1. And hey, quick pro tip here, do not forget to multiply by that little base area, the delta A, at the very end. It is such a common mistake, especially when the area is 1, and it feels like you're not doing anything. A Riemann sum is a sum of volumes, so you always have to multiply the height by the base area. And there we have it. Our estimated volume is 9. Now remember, this is an approximation. It's not the exact volume, but it's a good estimate. All right, last concept for today. Let's talk about finding the average value of a function. You can think of this as finding the typical or average height of the entire surface over the region. So for this example, imagine we're just given the total volume. We're told it's 50, and we know that the base of this shape is a circle with a radius of 5. Our mission is to find the average height. To do this,
We go back to that formula from our property slide. The average value is just the total volume divided by the base area. So step 1, we calculate the area of that circular base, which is pi times r squared, or 25 pi. Then we just plug everything into the formula. We take 1 over the area and multiply by the volume of 50.
And that simplifies down to 2 over pi. So what does that number actually mean? It means if you could take that total volume and smooth it out perfectly over the circular base, you'd end up with a cylinder with a constant height of about 0.637.
So we've learned the fundamental idea behind the double integral, and we've even seen how to estimate it with these Riemann sums. But an estimate is still just an estimate. So the big lingering question is, how do we find the exact volume? Well, that's the next step on your calculus journey, and believe me, that's where things get really cool.